Okay, looking at LC6. Continuity is great. Gotta love continuity. And one thing you might want to always look for on these limit problems is, wouldn't it be great if this function were actually continuous at the point that I'm approaching, because then I just plug in and it's the world's easiest calculation. So I like to always check for that first. Now, bad news, it's not continuous because the denominator is 0 at the point that we're approaching. Right? So disappointment, but it's always good to check for that, just in case. Now, we can start, parametrizing lines and parabolas and all sorts of different curves and try to prove that the limit does not exist. But maybe we'll get lucky and we can do this in polar. And notice this actually looks pretty nice in polar. That's x squared plus y squared, quantity squared. So that's r squared squared. So I claim this denominator is r to the 4th. Simplifies fantastically. And so I'm optimistic that this will simplify okay altogether. Let's work that out. So we're taking the limit. Now as r approaches 0, and I have, let's see, x cubed y squared minus x y to the 4th all over, well, let's see, now we already agreed that was r squared squared, so the denominator is r to the 4th. And the good news is that we have at least 4 powers of r in both terms in the numerator, so this becomes limit r approaches 0. We have an r to the 5th over here. We have an r to the 5th over there. That cancels all this r to the 4th, and there's an r left over. So I have r times cosine cubed theta sine squared theta minus cosine theta sine to the 4th of theta. And this may be a lot to write down, but it's bounded. This is approaching 0, and we take something that's bounded and multiply by something that's approaching 0, the limit is 0.
By bounded, it's just between 1 and
It's always between, well, in this case, between 2 and -2. Yeah, exactly. In other words, it can't run off to infinity. In other words, as r is in the process of, this is not some sort of indeterminate form, in other words, where, well, yeah, that's approaching 0, but this could be running off to infinity. No, it can't. Yeah, it's on a leash.
Gotcha.
Yeah. Exactly. So this is one of these awesome little, it's so cool when it happens, polar problems. You want to always be on the lookout for these as well. I like to always check for continuity first just because it's so easy, right? And all you have to do is you pretty much look and see, well, is there anything in the problem that would, is there anything discontinuous in the whole problem? And the only thing that has any potential for possibly being a discontinuity is the fraction. And you have to check and make sure the denominator isn't 0. And okay, tragically, the denominator is 0. But look how easy that was to check. Casual glance. So I like to always do that first, even though it didn't work out in this case.